Well, today we'll be talking about matrices. I'm covering it just for the sake of introducing you to what they are, or maybe just a reminder of what they are. I don't believe they will be in the standardized test for any of the states that I'm familiar with. So if you or your instructor don't feel you have any need for this, don't watch it. It's going to be pretty short. It's really just to remind you, and if you've completely forgotten or never took the first class, introduce you to matrices and what they are and how they work. A matrix is basically just an array of numbers. For instance, if I write the number 4, 2, 5, 1 and go like that, that's a 2 by 2 matrix. They don't have to be square either. I could have written 4, 2, 8, 5, 1, 9. They don't have to be square. They don't have to be 2 by 3 or any other particular dimension. You could have 20 by 20 if that's what you wanted, if that's what worked for you. These, the 4, 5, and 2, 1 here, this part, call this like that. That's a column. That's a column. Well, there's supposed to be a 1 in there, sorry. Well, this part here, these are rows. So if you look at it, you've got rows of numbers, or you've got you've got columns of numbers, or you've got rows of numbers, depending on how you look at it. These are the rows, these are the columns. Get it? Row, column. Those are very common expressions. If you're going to refer to matrices, you're normally going to have to be able to refer to columns and columns and rows. So you need to know what people are saying when they talk about rows and columns, and that's it. The up-down part, that's the column. Kind of like what you'd expect. I mean, big buildings have columns out front that hold up the roof. Well, same thing. These are columns. They don't hold anything up, but they're vertical. They're columns. The rows, those are the horizontal ones. Why in the world would you want a square full of numbers? Or a rectangle full of numbers? Well, it turns out that they're extremely useful in solving systems of linear equations. They're also useful in more advanced forms of transformations. In fact, a matrix can be defined as a transformation, which is more advanced mathematics. We're only touching on some of the things in here that you're going to see much more of later on. For instance, when we did trigonometry, gee whiz, we spent a day or two on sines and cosines and tangent functions. In a real course in trigonometry, you would spend about 3 months. You would also learn the inverse functions, but trigonometry is a good 3-month course. There's a lot to it. Matrices, well, they're part of linear algebra. You could take a single course which teaches computational use of matrices. Engineers use that a lot. If you want the more theoretical approach, that's 2 courses. That's like 6 months of college study of linear algebra to completely understand matrices. And we're just going to go over it for 30 minutes or so that you're introduced to what they are, how to add them, and how to multiply them. And when you see it later on, it won't be like a complete shock to you. Other than that, it won't get used much in this book, and I seriously doubt that it will be on your standardized state exam. So if your instructor or homeschooler tells you to completely skip this part, they probably know what they're talking about. What about addition? Suppose I have something like an extraneous mark on a page. Oh, that's not what I wanted. There we go. Suppose I have something like a matrix. We'll say it's 2 by 2. One of the easiest things you can do in this is multiply it by a single number. It's also called a scalar. Suppose that number is maybe I'll use an actual number. Yeah, we'll call it an x, what the heck. Suppose I want to multiply by a single real number here. This is not a vector. It's not a matrix. It's just a real number. Also called scalars. And this, you can put a dot there if you want, but the concatenation. Remember, concatenation is when you put two things right next to each other, like A, B. A and B are concatenated. Not really important at the moment. This implies multiplication, and what's the result of this? Well, it's another matrix, but the matrix now has entries equal to this. Pretty simple, right? You just multiply each element in the matrix by the real number on the outside and end up with this new matrix. That's multiplication by a single number. Real easy. In fact, it's just like what we were doing when we multiplied a ratio by a number. Remember, we just distributed it across all the numbers in the ratio. Same thing. What about if we want to add two matrices? After all, these matrices are just made up of a bunch of numbers, real numbers, and we can add and subtract real numbers, so shouldn't there be a way to add and subtract matrices? And there is. If I have two matrices and I want to add them up, well, couldn't be simpler. It's almost exactly what you'd expect it to be. It's just like when we added vectors, really. If you got a vector, AB, and another one, XY, how did we do it? We just added up component-wise. So we got x to the a, and we got y to the b, and get our new vector, a plus x and b plus y. Well, we're going to do the same thing here. We're going to get a new matrix, which is a plus w, b plus x, c plus y, and d plus c. So when you add up these two matrices, you do pretty much what you would probably expect to do. Just add up their respective components. Add w to a, x to b, y to c, and z to d, end up with this new matrix. And this is called the sum of these two matrices. If this is matrix A and this is B, then we would say this is the sum of A and B. Well, okay. That's addition. Subtraction? Well, exactly the same thing. Just pretend that you're adding a negative. And remember from this, suppose this x was minus 1. Then this would become minus A minus B minus C minus D. So if we put this matrix plus minus 1 times this, that's the same as subtracting. And all these signs would become negative instead of additive. We'd have A minus W, B minus X, and on down the line. Again, just add or subtract component-wise. Real easy. So we can very easily add and subtract matrices. What about multiplication? After all, these variables in here just represent ordinary real numbers. And since this is an array, these are both arrays of real numbers. Might there be a way to define some kind of multiplication between these two? It turns out there is, and it is definitely not obvious. What you do is, you multiply each row component-wise by each column. In other words, it's kind of weird, isn't it? You multiply A times W, and then B times Y, and add them together. This is going to look totally strange to you if you haven't seen it before. We got AW plus BY And that's only the first component of our new matrix. Our next component, see, this is the upper left. Our upper right component is the first row times the second column. That's AX plus BZ. Now, our next row for our new matrix is this row times this column, and then the next entry will be this row times this column. In other words, for the first matrix, you just go down the line one row at a time and multiply that row by each column, and that gives you your new row in your resultant matrix. Now you go to your next row, and we get CY that's not right, pardon me. It's CW plus DY, and this entry, our bottom right, that's going to be this row times this column, so it's CX plus DZ. Kind of strange, isn't it? This is one entry here. This is one entry. This is one entry, and this is one entry. And we're going to work some problems with actual numbers to help you make sense out of this. But the hardest part to remember is that it's row times column. Row times column. Well, that's multiplication. What about division? Forget it. That's the short answer. In reality, there is a way to divide matrices, but we're not going to go into it because it's super complicated. I mean, look at how complicated multiplication is. Remember, division is just multiplication by the inverse. So the first thing I'd have to do, if I wanted to divide, well, let's try it. If I want to take AB, this matrix here, we'll call it, let's say this is matrix A, okay? If I want to take matrix A and divide it by matrix B, I want to come up with some expression, in other words, for not A times B, but A over B. Well, this is just the same as A times B inverse, isn't it? Or 1 over B. These two are the same thing. So if I want to divide by matrix B, what I'd have to do is write out the matrix, and multiply by the inverse of this matrix. What is the inverse of this matrix? Who knows? It's not an easy thing to figure out. Number one, for ordinary numbers, like we've been using up till now, if A and B are inverses, then A times B equals 1, right? For instance, if B was the inverse of A, then B would be the same as 1 over A. We'd have A over A, and that's 1. That's almost, that's like a definition of inverse. A times A inverse equals 1. Well, what are we going to multiply this here by to end up with 1? And what does it even mean to be 1? I mean, these are matrices. 1 is just an ordinary real number. Well, that's why it's so complicated, because in matrices, 1 is written like this. In a 2 by 2 matrix. I think it's like that. I better double check. Let's suppose we call that 1. Why would we do that? Well, in general terms, what is 1? As an algebraic identity, any number x multiplied by 1 just gives you back x, right? So it's also called an identity. This 2 by 2 matrix takes the place of an identity. in 2x2 matrices, in the world of 2x2 matrices, this is 1. At least I think it is. It's either a 1 here and here, or a 1 here and here. It's 1's on the diagonal. And there's an easy way to find out. All I have to do is take a matrix and multiply it. So let's find out. Let's see what would work as an identity. In other words, what would perform the function of 1, but with matrices, not real numbers. Well, let's see what we've got here. We got AB, that's the row times the column. So we got A times 1 and B times 0. So that's A. We got AB times 0, 1, so we get A times 0 and B times 1. That's B. Over here, we get the row, second row times the first column, that gives us this entry here. And that's C times 1 and D times 0. And CD times 0, 1, we get C times 0 and D times 1. So, it's been a while, but I guess I guessed right. This is what takes the place as 1 in the world of 2x2 matrices. So what you have to ask yourself is, what in the world would I multiply this matrix by in order to get this matrix? If it's not obvious to you, well, good. If it was obvious, you'd be some kind of alien. But this stuff is actually pretty hard. I shouldn't say that. I mean, you might just be really smart. You wouldn't really be an alien. There are some really smart people for whom this stuff is obvious. But I haven't met any. Before we work problems, there's something else you should know about matrices. Remember I showed you how to multiply them, and it's row times column. Well, there's 2 more things you need to know about multiplication. These things have to match up. Notice that because this is a square matrix, they both are. When we take this row and, in a sense, straighten it and multiply it by this column, the components match up. Suppose I had another line down here that would say LP, and this was all part of the same matrix. In other words, extended like this. What the product of this matrix and this matrix doesn't exist. See, the way it works out is, since this is the first entry of a column going into this one, and this is the next column going into this row, the columns and the rows have to match up. In other words, if we've got 2 columns, here column 1 and column 2, then we have to have 2 rows, row 1 and row 2. That way, when you, in a sense, rotate this 90 degrees, put it up next to this and perform multiplication, everything matches up. If we had If we had 3 rows here and 2 columns, that would be okay. Oh, pardon me, that wouldn't be okay. Yeah, if we had 3 rows here, let's see. I gotta rewrite this so that you can understand what it is I'm trying to tell you. This would work. Seems weird, doesn't it? But here we have AB. We've got 2 columns, so the top entry in each column will match up with the first entry in each row. We get A times W and B times Y. Same thing here, because we have as many columns as rows. So however many rows we have here doesn't matter. Normally matrices are frequently, I wouldn't say normally, they're described as rows and columns. In other words, this would be called a well, that's not true. This square matrix is 2 by 2. And this matrix is 2 by 2. But if it wasn't square, if we got it like this, This is 2 by 3. Set it backwards. Row, column. It's written like this. Row by column. So this one would be 3 rows, 3 by 2. This one is 2 by 2. All you have to keep in mind when you describe your row by column, is make sure that these two numbers here match up. This could be 5. In other words, we can have any number. We could have 10 by 2 matrix multiplied by a 2 by 7 matrix. That would work because these two match up. This means we have 2 columns, just like here, and we have many rows as we want this way. Here we have 2 rows, but we can go out this way. So there are definite restrictions on matrix multiplication. There are many, many matrices for which the product is simply undefined. You can't do it because the rows and columns don't match up. We need to have the same number of columns in the first one as rows in the second one. Wait a minute. Multiplication is commutative. So what difference does it make which is the first one and which is the second one? Well, what you know about multiplication of real numbers doesn't quite work with matrices. Matrix multiplication is not commutative. And let's take a look and we'll see why that's true. Here I've written the product of these two matrices out again. And remember, it doesn't matter. AW and WA, these are real numbers in here. So the individual entries, multiplication is still commutative. But it's just when we reverse the order of the matrices themselves, we end up with a different matrix. And well, let's see what happens. Here, okay, we get AW plus BY. The next entry is AX plus BZ. Here, CW plus DY and CX plus DZ. Well, what's our first entry in this one? AW, AW. These two are commutative, so that's fine. But what about the next entry here? X times C. Well, our second entry in this one, our second, or rather addition part, is BY. Well, XC and BY aren't the same thing, so this entry, upper left entry, not the same. What about this? Where we get WB plus XD. Here we get AX plus BZ. Again, not equal. And you can go right down the line and look at these and realize that as you change the order of the matrices, you go from B times A to A times B, if we call this matrix A and this B. And then this is A and this is B. Well, we have something that we probably haven't seen before. And that is A times B does not equal B times A. Which turns out to be a good thing. if in matrix multiplication A times B equaled B times A, it would be like allowing division by zero. The universe would explode. It turns out, for instance, in physics, all the interesting stuff happens in the difference between AB and BA. Some matrices actually do commute. There are some special matrices for which AB does in fact equal BA. For instance, I showed you, well, that's kind of not fair, but like I showed you the identity matrix. If A was the identity matrix, A times B equals B, and B times A equals B. And there are some other matrices which will commute, but they're special cases. In general, you can't say that matrices commute, and it's a good thing that they don't. If they did, the world would explode. So let's try a specific one here. What do you think that's going to turn out to be? Well, addition is extremely simple for matrices because it works out about the simplest. If you were looking for a simple way to do it, it's like, I don't want to have to remember much. How would I define addition? Well, I think a useful way would be just add it up component-wise. Add up the 12 and the 2, the 5 and the 3, the 1 and the 0, and the 4 and the 8. And that's exactly the definition of matrix multiplication. So this is 10 minus 10. And 5 plus or minus 3, that's 2. 1 plus 0 is 1. Minus 4 plus 8 is 4. See? That's, if you can add two numbers, then you can add matrices. It's very easy. There's supposed to be a minus 10 there. Now here's a couple of special kinds of matrices that I didn't mention. Remember I talked about rows and columns? Well, this kind of looks like what we used for a vector, isn't it? We would write 5, 2 like that. Well, it turns out they're exactly the same thing. You can think of this as a row vector and this as a column vector. It's frequently referred to that way in other textbooks that use matrices much more in vectors, which gives us a way to multiply vectors. We didn't talk about vector multiplication in the previous section, even though we introduced vectors. But here we have, well, what is this? Row, column. This is a 1 by 2 matrix here. And what's this one? 2 columns, 1 row. This is a 2 by 1. Remember, the inner numbers have to match up. So we can multiply these two. We just, in a sense, turn these sideways and match them up. So it's 4 times 5 is 20. And the next entry in our first row is 2 times 3. What's next? Well, nothing. We've used everything up. We've only got 1 row and 1 column. And that gave us, oops. Yeah, that's right. Pardon me. So if we perform the actual matrix multiplication, we get the first entry is 5 times 4 is 20, plus 2 times 3, which is 6. And what's the next entry? Well, there isn't any more. We don't have any more columns to multiply this row by. So the answer here is 26. That is, this row vector times this column vector is equal to just an ordinary old number called 26. It's not a matrix. Interesting, huh? And in fact, all we really did was we took the vector 5, 2, multiplied it by the vector 4, 3. Doing it this way, where you just multiply the components and then add them together, that's called the dot product. We're not going to use that at all in this course, but you might as well know the name for it, dot product. I know it's might be kind of confusing because we frequently use the dot to indicate multiplication. In this case, we're talking about a very specific form of vector product. Why distinguish it? Why not just call it a vector product? Because there's something else that is called a vector product. You see, we've multiplied these two vectors. We just got a plain old real number. There's another way to do it. In fact, there's two more ways to do it that will give us another vector. One kind of multiplication gives you a vector that's perpendicular to both of these vectors. And in this case, there's a third kind of multiplication, because you could also represent these two-dimensional vectors as complex numbers and then use complex multiplication. Yeah, I'm probably confusing the heck out of you, so don't worry about most of that. All you need to know is that we call this a row vector, this is a column vector, and when we use matrix multiplication, we're essentially generating what in other classes will be called the dot product of two vectors. And it gives you just a simple scalar. If we had two rows here, or pardon me, two columns on the right hand side, then we'd have two entries here, and this product would give us a row vector. See, these inside parts have to match up, and the outside parts give you the dimension of the resultant vector, or matrix. Did that make sense? These two have to match up, or otherwise the multiplication is not defined. If the multiplication is defined, these outer numbers here tell you the dimensions of the resulting matrix. For instance, I said I could add rows or columns here, right? And it would still be defined, because I would just be multiplying this row by this column, then another column, then another column. That would be fine. So this last number could be anything, and when I got done, I would have a 1 by however many columns here, vector. So if I added columns here, if I added two more columns, then I would have two more entries here, and it'd still just be one row. Over here, if I added rows, I could do that, and what I would be doing is adding columns to this one, and I would end up with a column vector. Yeah, it's pretty confusing, but all you can do is fool around with it, and that's not as much fun as you might think, because these numbers are kind of clumsy. Matrices are kind of clumsy when you start multiplying large matrices. 3 by 5 by times a 5 by 3 matrix. Well, that ends up with a whole bunch of terms, doesn't it? And a whole bunch of things you have to add up. Here's one that's like what I was talking about. What is this in dimensions? It's 2 rows and 3 columns, so this is 2 by 3. What is this one? Well, 3 rows. Each one of these individual entries counts as a row, but only 1 column. So this is 3 by 1. These are not square matrices, but the inner numbers match up, so we're okay. In other words, the rows and the columns. The columns in the first one and the rows in the second one have to match up. And you can tell just from this that the result is going to be a 2 by 1 matrix, meaning that your resultant matrix should have 2 rows and 1 column. Let's see what happens. What's the first entry? 9 times 4. Is that 36? Yeah. 36 plus 1 times 0. 0 plus 2 times 1. What's our next entry over here? Well, we don't have one because we don't have another column. So we're done with this row. Now we just have to drop down to this row. See, what you do is you take a row and multiply by every column you can find. When you run out of columns, you're done. Well, after multiplying by 1 column, we're done. That's all there is. So now we multiply by another column to get the next row. and that is 8 times 4 is 32. Anything times 0 is 0. And 4 times 1. So what do we end up with? And that is a column vector which has 2 rows, 1 column. So it's totally legitimate to multiply matrices that aren't square. Just have to match up the columns and the rows, because you're in a sense going to take this row, turn it sideways, and match it up against the column. So if we don't have an entry at the beginning of each row for each one of these columns at the top here, the top of each column and the front of each row, if they don't match up, then we're out of business. Here they'd like to know which product is not defined. Well, I showed you the easy way to work this out. Just write down the dimensions in row column. Remember, that's R cross C, row column. So how many rows do we have here? 2. How many columns? 2. How many rows do we have here? 2. 1 column. They match, so this is okay. What about this one? We have 1 row, 2 columns. Here we have 2 rows, 1 column. In fact, we just did one like that, didn't we? A row vector and a column vector. That works. That's okay. What about this? We've got 2 rows, 1 column. Here we've got 2 rows and 2 columns. Uh-oh, that doesn't look right. What about this one? Yeah. I'm in the habit of double checking. We've got 2 rows, 1 column, 1 row, 2 columns. Oh, they match. This one's no good, because there's no way you can do this. You lay this thing sideways. Well, the row only has 1 entry, so how do you multiply 1 entry by these 2? You get 15 times 1 plus something that doesn't exist times 4. I mean, if you want to extend this and make it 15, 0, and 3, 0, well, now you might have something, but you can't just automatically treat nothing as 0. I know that sounds strange to you, but in mathematics, 0 and nothing aren't quite the same thing, and especially in programming. Don't ever confuse 0 with null. Null is nothing. 0 is something else. 0 is a definite number with a meaning. Null just means empty, like an empty universe or something. There's just nothing there, like a huge vacuum. 0 and null aren't the same thing. And the fact that there's nothing here to the right, or say in this one to the right, it doesn't mean we just stick zeros in there and say it's the same thing. It's not. 15, 0 and minus 3, 0 would definitely not be the same matrix as 15 and minus 3. For instance, you can't just throw that 0 out there. This 0 right here. You can't just throw it out and say, well, it's only 0, so it doesn't matter. You can drop it. And no, it won't work. In fact, if you do that, you got nothing, because you have to at least complete your rows and columns. They don't have to be equal, but they have to be finished. You can't have a row with 2 entries here and then another row with only 1 entry. That's not allowed in matrices. Now here we have error, and this is, might be a common mistake. It's an easy thing to do. What did you do wrong here? Remember, it's row times column. Row times column. So we get 9 times negative 6. That's fine. Plus minus 2 times minus 6. Minus 2 times what? No. That's no good. What about this one here? 4 times minus 6. No, gee, you got this all messed up. what he did was he multiplied the row by the rows. He put 9 times minus 6, 2 times minus 2 times 12, 4 times 3 in other words, he treated it kind of like addition. If we were adding these two matrices, you would simply add up the corresponding components. 9 and 6, minus 2 and 12, 4 and 3, and 10 and minus 6. Multiplication is a completely different animal. The first entry should have been 9 times minus 6. Is that minus 54? Plus minus 2 times 3. The next entry, because we're going to end up with the 2 by 2 matrix. The next entry is 9 times 12, at 108. And minus 2 times 12, which is minus 24. And down here, lower left entry, 4 times minus 6 is minus 24. Plus 10 times 3, that's 30. And then 4 times 12, that's 48. 10 times minus 6, minus 60. So we got, I think that's minus 62. Oh no, wait, minus 24. Let's see, that's 88 minus 4 is 84. 24. Oh, minus. Okay, that's minus 6 then, unless I made an arithmetic mistake. And 40 minus 60 is minus 12. Doesn't look much like this, does it? This would have been minus 54. This would be minus 24. This would be minus 60. And this would be 12. And there's almost no relation to this matrix in any of this. So it's important to remember, with addition, just match up the components. Real easy. Multiplication, whole different thing. You multiply the row by the column, and you add them up, of course. So it's like 9 times minus 6 plus minus 2 times 3, and you get this. Do that all the way through, and you get a bunch of complicated stuff that ends up looking like that. Now let's take a look at one more thing with actual numbers inserted. Suppose we have 3 matrices. A, which is the same here and here, and then B and C. So what do we have here? We've got A times B plus A times C. If we multiply that out, what do we get? We get 1 times 3 plus 2 times 4. And it's up here, that's 11. Next entry is 1 times 7 plus 4 times 1. That's 11. We take our second row times our first column and get 15 plus 4. It's 19. Our second row times our second column, we get 35 plus 2, 37. We do the same thing over here. 1 times 4 plus 4 times 7. On down the line. So this matrix, when we add it up, turns out to be 11, 11, 19, and 37. And A times C is 32, 14, and 34, 16. Now we add these two up. So this is AB plus AC. We add them up, we get this matrix here. 43, 25, 53, 53. We have the same matrix here. So what if we had done this? A times B plus C. In other words, just like with real numbers, suppose we had added the numbers up first and then multiplied, as opposed to multiplying and then adding. What would happen? let's try it. Here we have A, and here's B and C again. Well, we add these up, and we get our new result matrix for the sum is 7. 3 and 4, 7 and 2 is 9, 2 and 7 is 9, 1 and 3 is 4. There's B plus C right here. Multiply it by A, and we get this matrix. And when we perform the additions, 7 plus 36 is 43, this is 25. Well, let's compare it to what we had before. Uh-oh, looks the same. Here's the first row, 43, 25, 43, 25. Next row is all 53s. Well, this isn't a proof because we just used numbers. If you wanted to do a proof, you'd have to use variables. That would take a real long time. You can imagine how messy this would be if you actually used variables. In all of these, you'd have tons and tons of just long strings of things. You could do it. But I will tell you it's a fact that matrices are distributive, and using particular numbers, as I say, it's not a proof, but it may help you believe that it's true. You can, when you end up with something like A times B plus A times C, you can rewrite it as A times B plus C. Well, that's about it for matrices. Obviously, this was kind of abbreviated. Like I said, matrices are big, they're really important. This, well, I guess next time you see a matrix, it won't be a complete mystery to you. But other than that, this was actually fairly short, and like I say, it may not even be on the standardized test. So check with your instructor or homeschooler. You may not even need this video for anything. On the other hand, if you're curious how they work, well, this is how they work.